Hey everyone, today we have got a 3D scan of an automotive Fender flare sent in by one of our viewers from this channel. I think the owner's hoping to replace this part with 3D printing. Looking at the original, I can see some damage. The wall's a bit warped and one of the mounting holes is twisted. Luckily, all of that can be fixed by remodeling it in CAD, which is basically what we call reverse engineering. And here comes the big question everyone asks: how do you even model this? The part curves in every direction and twists along its length. That's basically no flat surface anywhere. And on top of that, the flare has all these little flat indents across the surface, which makes it even trickier to model. And that's not all. The owner made things even tougher by only scanning half of the flare. Yep, just the inner wall. And to top it off, the scan quality is pretty rough, a thick wall, and a lot of noise. And in this video, I'm going to tackle the reverse engineering using BricsCAD. Let's see if it can handle such a tough modeling challenge. In my experience, here's basically what you need from a 3D scan if you want to get it ready for printing. First off, you need a 3D scanner that gives you a real usable resource, precise enough to align multiple scans and produce a sharp, accurate, noise-free point cloud. For me, the Raptor Pro is the best performer for its price right now, and if your part isn't too big, you can always start with the cheaper Raptor Original. I have worked with scan data from RiverPoint's scanner, and honestly, I'd never seen one that's both precise and noise-free. The Star 2 I tested gave a nice clean scan, but the precision was too low. You couldn't align multiple scans together. This is just my professional opinion. I have never received any commission or payment from Clarity or from any of the products I review in this channel. Next, you need CAD software that can import point clouds and give you all the tools for solid and surface modeling. Right now, BricsCAD is the best performer for its price, and in this video, you will see how well it handles modeling. The price here is a one-time lifetime fee. If your work doesn't come in steadily, you really shouldn't have to deal with a subscription. And finally, the 3D printer. For recreating automotive parts, you want the biggest enclosed printer you can get with a heated chamber for high temperature plastic. Automotive materials loading isn't really necessary, but a filament dryer definitely is. So all in, this setup will cost you around $5,000 US. If it's just a hobby, that's definitely on the pricey side. But if you are running an auto shop, it's more of an investment in professional capability. You have probably never heard of a BricsCAD before. When people talk about 3D printing, they usually mention CloudCAD tools like Fusion or Onshape. But BricsCAD has actually been around since 2004, so that's 22 years with over 300,000 users, and the point cloud import was added in 2018, and it runs smoothly without any lag. It's got all the creation tools, sketch tools, and sketch foundation tools you need to build any geometric shapes. Here's my plan. I will create 2D cross-section sketches along the length, right at the points where the shape changes. That way, the 3D rails will run smoothly. And I'm going to use 3D splines as the rails to drive the shape. So the main tools I'll be using are Loft with a bit of extrusion and some surface patching. In BricsCAD, it works like an AutoCAD style CAD tool. You start by creating 2D sketches over the XY plane, but it got tools that let you move and rotate the sketch plane or UCS to any spot and orientation in 3D space. It's also got a full set of snapping tools, tracking tools, and even point cloud snapping. It also got a dynamic UCS for auto-detecting planes, plus the push-pull command that lets you extrude directly on a face. It also has direct editing features so you can work right on the solid plane itself. And when it comes to surface modeling, all the tools are right there. Honestly, you can create just about any geometric shape with it. I have modeled half of the flare since it's pretty long. Now I'll show you the next loft sections. Start by cropping a thin section of the point cloud, then snap a UCS plane onto the cutting edge of that cloud. Trace a 2D sketch on the XY plane, then offset it by 3 mm to set the wall thickness. I skip the fillet corners to keep the modeling process faster. After finishing the sketch, I use the join command to close the loop. Then I just make a copy of the sketch to use for the next loft. I snapped 2 points on the corners of the sketches to set up a UCS along the Z-axis. Then I created a spline with 3 control points tracing along the blue tracking line. I adjusted its shape by moving the control points along the X or Y axis. I copy the spline and place it on the outer wall, stretching it if it's too short. This kind of direct copy isn't possible in Autodesk Inventor. This workflow in BricsCAD lets me create 3D splines quickly, and I can copy them to build a parallel wall. I will hide the splines so they don't block the view while I'm creating the next one. Moving the spline control points along the X or Y axis is super fast and easy, so I can add as many rails as I need. When I do this in Autodesk Inventor, I have to set up a 3D sketch, include the geometry, add control points, and only then can I start adjusting the spline. You might notice the scan data looks noisy and a bit unsharp, which makes tracing harder. But this Fender flare is a great example to test BricsCAD modeling power. The scan was done with a remote point scanner. I can't remember which model. Now that the 3D lines are done, I will go ahead and loft between the 2 sketches using the splines as guide rails. The 2D sketch is already used, so I will just drop the copy back in the same spot. I'll pick this spot for the next cross section since there is a bump right here. From here on, I will speed things up since each loft step is pretty much the same. You can rotate the UCS Z-axis so the control point moves exactly in the direction you want. Here's the second loft profile. It's a separate body from the first one, but once the modeling is finished, you can weld them together with a single click. You can change the point cloud color right in BricsCAD, matching it to the layer's color. The next loft section is pretty short. I made a sketch lie on the drop it floor spot, so you need to find the right place to put it. In this loft section, I'm picking the spot right at the end of the curved wall. Since the scan data only shows one side, I'm giving the whole model a constant 3 mm thickness. You can see that with all these 3D rails, the loft command runs perfectly smooth. I would say that the loft command actually works better here than in Autodesk Inventor. For the next loft, I will flip the sketch orientation and loft downward. That way, I can capture more of the detail in the section profile. When the loft direction changes like this, you will need to make a new sketch from the plane of the previous loft. In this case, I flipped the plane 90 degrees from the last loft surface, which makes the new loft connect seamlessly. The next downward loft is a short one. I picked this point for the sketch because there is a bump on the wall. Here's another short loft section. I had to add an extra rail because the sketches don't have the same number of corners. Even with lots of rails and a complex shape, I haven't run into any errors using the loft command. I make about a 45-degree turn for this loft section, so it gradually joins the lower part. This section uses over 10 rails, and once again it works flawlessly. One tip: if you want to round corners with fillets, do that before welding the sections together. I've made a mistake of welding before adding the fillet. After saving and reopening the file, I couldn't go back to the earlier step. Here's the final section where the downward loft meets the horizontal one. The shape is pretty complex with more than 10 rails guiding the surface, but once again it works flawlessly. This isn't a full tutorial video. I find a proper example to show reverse engineering of a complex shape in BricsCAD. Here's a final loft section at the top. To finish this part, I pulled up the solid and made a quick sketch to cut through it on two planes. BricsCAD lets you align the wheel and set the UCS plane right from the viewport. I have found this works great for reverse engineering. I use this approach to cut two openings here, since you can perfectly align the UCS view with the point cloud. Once all the modeling is done, I will use the union command to weld the solid bodies together. Finally, I show you how to make a shallow indentation on a curved surface. First, extract the surface from the solid, then draw a cutting profile and extrude it. Next, use the intersection command to combine the surface with the cutting solid. Now, you have got a matching surface right on top of the solid. Then I use the Thicken command to turn the surface into a solid with a thickness I want, and finally I use it to cut into the part I want. Here are my thoughts on using BricsCAD for reverse engineering a complex part. With its AutoCAD style workflow, BricsCAD makes modeling fast and flexible. You can create 3D lines quickly, unlike Inventor style CAD where you need to set up a project, create a part, then build 2D and 3D sketches before you can start modeling. BricsCAD demonstrates superior efficiency when manipulating point clouds, offering faster cropping and more precise alignment. This works because you can move the point cloud together with the sketch. Let's check the result with ray tracing. The surface looks smooth with no sharp or standout edges. The curve continuity is good even without applying a tangent constraint. Modeling in BricsCAD is easy and trouble-free. It could be an ideal CAD tool for workflows from 3D scanning to 3D printing. BricsCAD provides me with a demo license, so I'll be running more reverse engineering tests in the future videos.